हॅलो सर. हॅलो.
हा सर. हा
हा आवाज येतोय ना?
हो येतोय सर.
ठीक आहे. हॅलो.
मी जरा मीटिंग मध्ये आहे सर, आता थोडा नाही करतो, 12 वाजता करतो कॉल तुम्हाला.
हॅलो.
हा गुड मॉर्निंग सर.
हा गुड मॉर्निंग सर. आर यू गेटिंग मी सर?
Yes, yes, yes.
Okay. Can I proceed now, sir?
Yes, yes, yes. No problem.
Okay, thank you, sir. Friends, welcome back to today's special guest lecture, jointly organized by the Physics Department of MSP Wonders Arts, Commerce and Science College, Kille Dharur, and Shikshan Maharshi Mahavidyalay, Nandya Mohekar Mahavidyalay, Kan. First, I would like to introduce the today's resource person. His full name is Professor Dr. Vivekanand Baburao Kavade. Honorable Professor Dr. Vivekanand Kavade is working as a professor and head of Physics Department of Late Lakshmibai Deshmukh Mahila Mahavidyalay, Parali Vaidyanath. Friends, he is well known in this Marathwada region for his hard work and sincerity. Honorable Dr. Kavade sir has a bulk experience of 22 years for UJ and PG classes. The students has completed their PhD degree under his able guidance. The Dr. Kavade sir has published in all 21 research papers in various national and international journals. Out of these, the 13 papers have presented in various national and international conferences. 10 papers are presented in national conferences and 3 papers are presented in international conferences. Again, Dr. Kavade sir is active in various professional activities. Dr. Kavade sir is a life member of Indian Science Congress Association, life member of Indian Association of Physics Teacher, participated in Indian Association of Physics Teacher, the participated in one-day National Conference on Innovation in Nanomaterials and Nanotechnology in 2017, participated in one-day National Conference on Advances in Chemical, Physical, Agriculture and Life Sciences for Rural Empowerment held at Vaidyanath College, Parali Vaidyanath, participated in 103rd Indian Science Congress held at University of Mysore from January 3rd to 7, 2016. Honorable Dr. Kavade sir has worked as a BOS member of our Dr. Babasaheb Ambedkar National University, Aurangabad, and he has a leading role in the designing of course and curriculum of BSc classes. He has designed BSc first year syllabus in 2012 and 13. Again, he has designed BSc second year syllabus in 2013 and 2014. And he has designed BSc third year syllabus in 2014 and 2015. Friends, I hope this is sufficient to well known our today's resource person. Apart from this, I would like to highlight some points about Honorable Dr. Kavade sir. Friends, Honorable Dr. Vivekanand Kavade sir and I belongs from the same umbrella. That means we have completed our research work under the guidance of most eminent scientists, and he has received the world rank third among all the scientists. That means I am going to mention about my honorable guide, Dr. Professor Dr. K. M. Jadhav sir. And Kavle sir and I have completed the research work under his able guidance. Dr. Kavle sir is a senior research fellow for me. In the research period, when I find a difficulty, I find his cooperation. Then, without any hesitation, he provided me his helping hands. Many times he motivated, encouraged me. Friends, indeed, he is has a great sympathy. He is an open-hearted person. Certainly, I will be great experience for us to hear him. Now, I request Honorable Dr. K. Kavli sir to deliver his today's guest lecture on the title, The Semiconductor Devices and Their Applications. Honorable Dr. Kavli sir.
Thank you, Jadwar sir. So today's my topic is semiconductor devices and its application. So first of all, good morning to Jadwar sir, his team, and all the participants. Now I choose this topic due to the demand of semiconductor material from during these days. One big project, also shift from Maharashtra state to Gujarat state, that is Vedanta Foxconn, and this project is also related to the semiconductor material. So the material of semiconductor has a very less stock. This material we have to uh, get from the Taiwan country. This is the largest big one country to produce this semiconductor material, and whatever may be the chip required, we have to all the world purchase from the Taiwan country. So I starts my today's talk. Just 2 minutes. Minimize. Just. Stop sharing. Hey. Yes. So can you see the PPTs? Yes.
Yes, sir. Yes, sir.
Yes. Okay. So I am divide this lecture in 3 parts. That is semiconductor material, how to form the semiconductor material, how to distinguish insulator, semiconductor, and conductor. After that, the applications of the semiconductor materials, the devices, the semiconductor devices, and later on, we discuss some semiconductor devices which are very useful for mobile, computers, and vehicles also. So, on the basis of electric conductivity and valence electron materials, the materials are classified actually into conductor, insulator, and semiconductor. So can you tell me what is the conductor? So conductors are the material as per the outermost orbit electrons is called as a valence electron, and this valence electron plays a very, very important role for the characterization and properties of the material. So when the last orbit electron, that is valence electrons, are less than 4, means outer orbit electrons, the number of outer orbit electrons are less than 4, then that materials are called as a conductor. Now the conductors are sodium, magnesium, aluminum, these are the conductors, because in sodium, atomic number of sodium is 11, means in the last orbit there is a one electron, two electron, one or two electron. Magnesium atomic number is 12, and aluminum atomic number is 13. So in aluminum there are last last orbit electrons are 3. So these are the conductors. Now insulators, the valence electrons which are greater than 4, then that materials or that substances are called as a insulator. The nitrogen, whose atomic number is 7, so last orbit electrons are 5. Sulfur, neon, these are the examples are the insulator. And when the last orbit electrons are half of 8, that is 4, means in the last orbit of electrons is 4, then that materials are called as a semiconductor. So we know the carbon, silicon, germanium, these are the semiconductor materials because the valence electrons are 4. In carbon, there are the atomic number is 6. For silicon, atomic number is 14, and germanium atomic number is 32. So in these materials, the last orbit electrons are 4. So these are the semiconductor materials. Now, these semiconductor materials are again classified into intrinsic semiconductor and extrinsic semiconductor. So, see here, the structure
Hello,
of the
sir.
intrinsic semiconductor means pure form materials, pure form semiconductor materials are called as a intrinsic semiconductor.
Hello,
These
Kamal sir.
are, hello, Bola.
Sorry for interruption, but your screen is visible to us, but the slides are not visible.
मला विद्यार्थी म्हटले दिसते म्हणून मी पुढे चाललो.
फक्त स्क्रीन दिसते सर, त्यावर फक्त हॅव अ नाईस डे ची ती जी स्क्रीन आहे ती दिसते फक्त.
असं आहे का?
हो.
अरे अरे, मग शेवटी गेलो का? मला हॅव नाईस डे ची माझी नाहीच आहे सर, तुमचीच आहे मग ती.
ओके, एक मिनिट.
तुमचीच आहे ती हॅव नाईस डे ची, माझी नाही आहे.
स्क्रीन शेअर होते पण मग
शेअर युअर एंटायर स्क्रीन वर क्लिक करा सर एकदा.
मला वाटतं ही स्क्रीन जाधवर सरांची दिसते खाली नाव गाडे सर.
नाही नाही माझी नाही हो.
परत एकदा मी म्हणजे हे करू बाहेर. हा येस येस येस, ती काढून टाका सर. ती कोणाची एक पहिलं जे हे कोणाची काढून टाका. त्याला मिनिमाइज करा. एक मिनिट मिनिमाइज करा. हा, आता ह्याच्या व्यतिरिक्त काय ही काढून टाका ना.
आपण शेअरच करणार.
हॅलो, हॅव अ नाईस डे ची कोणाची ही आहे सर?
गेली सर ती आता
गेली ना?
शेअर करा सर.
तुम्ही वरच्या साईडला आहे सर, ते वरच्या साईडला अजून. हा, आता गेली.
बरं, आता आली का माझी?
हो हो सर,
आली ना शेअर?
हो यस
दिसतंय ना?
हो.
ओके 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 ओके, राईट. थँक यू व्हेरी मच. So there are two types of semiconductor materials. One is intrinsic semiconductor, another is extrinsic semiconductor. In the pure semiconductor form, extremely pure is known as an intrinsic semiconductor. So this one with the diagram of this 3D crystal lattice of the silicon. So the 4 valence electrons are form a 4 covalent bond with its neighbor atom. So these are the covalent bonds of the silicon, and these are tightly bounded. So there is no any free electron to form for the conduction or to carry a current. So the conduction of current through this intrinsic semiconductor by both free electrons and hole. But these are the pure form, so the conductivity is very less. So silicon, germanium, gallium, arsenic, these are the examples of this intrinsic semiconductor. Now the second type is extrinsic semiconductor. These extrinsic semiconductors are achieved by adding a small amount of suitable impurity to a semiconductor to increase the conductivity of the material. So, what are the impurities? So there are two types of impurity. One is called as a pentavalent impurity, and another is called as a trivalent impurity. And this process of adding impurity in a pure semiconductor is known as the doping. So depending upon the impurity added in intrinsic semiconductor, means pure form semiconductor, these semiconductors are classified into again two category. One is a n-type semiconductor and another is a p-type semiconductor. So pentavalent impurity is added in a pure semiconductor, then we have get a n-type semiconductor. The examples of pentavalent impurity is antimony, arsenic, and phosphorus. So arsenic has atomic number 33, means in the last outermost orbit of this arsenic there are 5 electrons. So for valence electrons, if we dope this arsenic in a pure semiconductor form, then 4 valence electrons of this arsenic forms the 4 covalent bond with this germanium or silicon and form a covalent bond. But one electron have no any vacancy to form a covalent bond. So this electron is a free electron. So this free electron we have to get for the conduction of the current. So doping of small amount of arsenic impurity provides enough number of atoms, or we have to supply millions of free electron. So in this way we can increase the number of free electrons in a semiconductor material, and these materials are called as a n-type semiconductor material. Now another second type is a p-type semiconductor material. So trivalent impurity is added to a pure semiconductor, then we have to get a p-type semiconductor. So what are the examples of trivalent impurity? Boron, gallium, indium. These are the examples of a trivalent impurity. The gallium has atomic number 31, means its outermost orbit there are 3 electrons. So these 3 electrons forms 3 covalent bond with the germanium atom, but in one covalent bond there is one deficiency of electron. There is no electron for this boron to form a covalent bond with this germanium. So this deficiency of electron is called as a hole. So in p-type materials, whatever may be the current conduction, that is with the help of hole. So in this way, when a small amount of impurity, trivalent impurity, that is boron, gallium, and indium is added in pure semiconductor, then we have to get a large million numbers of holes which are take part in the conduction. Means in n-type semiconductor, we have to get the electrons, and in p-type semiconductor, we have to get the holes. So after that, we discuss here some history about the semiconductor material. So Michael Faraday was first person to observe a semiconductor effect in 1833. And after that, in 1874, Carl Brown discovered first semiconductor diode effect. We know the simple p-n junction diode. So this p-n junction diode discovered in 1874 by this Born. And next there is a invention of rectifier by using this diode in 1874. We know that the rectifiers converts AC voltage into DC voltage. So this invention of rectifier we have to get in 1874. After that, Schottky invented the rectifier in 1875. So this invention of rectifier
सर तुमचा आवाज येत नाहीये. हॅलो.
बोला, त्याचा आवाज येतो तुमचा.
कवडे सर लेफ्ट जायत होते. जाधवर सर.
हो.
कवडे सर लेफ्ट झालेत वाटतं.
त्यांना कॉल केला मी एकदा, पण त्यांनी उचलला नाही. एक मिनिट बोलतो मी त्यांना.
ओके ओके.
तिथून पुढं हे झालेलं आहे का? अरे अरे अरे, मग लवकर सांगायचं किंवा मला सर. ह्या मी पुढे गेलोच नसतो ना इतका. हा दिसते का स्क्रीन? यस.
हा सर दिसते.
दिसते. आवाज येतोय?
हो हो.
बर बर, परत रिपीट करतोय मग मी. हिस्ट्री पर्यंत चालतो ना? यस. ओके. So over the last 70 years, semiconductors becomes a crucial element in the manufacturing of this electronics. And after the invention of transistor, the world of electronics has always been on the exponential curve in terms of research development, manufacturing, bringing up new devices and technology. So semiconductors are the backbones of the electronics. Now semiconductor devices are replaced vacuum tubes in 1980. Actually, vacuum tubes are vacuum tubes is again one of the device whose size is very large, and these vacuum tubes consumes a large amount of electricity, so they dissipate the heat. And the second drawback of this vacuum tubes is its size. So due to the size, the size of the electronic devices is very big, and the weight is also large. So we cannot carry these electronic devices easily. So in 1980, the vacuum tubes are replaced with the help of this transistor, and that's why the size of these electronic devices is reduces, and the weight is also reduced. So there are some common semiconductor devices, and these common services we categorize these semiconductor devices in three categories. One is two terminal, another is three terminal, and last is a four terminal devices. In two terminal devices, there are some important devices like diode, gun diode, laser diode, Zener diode, Schottky diode, tunnel diode, light emitting diode, photo cell, and solar cell. And in three terminal devices, bipolar junction transistor, field effect transistor, Darlington transistor, silicon control rectifier, thyristor, Tarac, MOSFET. And in four terminal devices in this category, there are again, we take here two example. One is photocoupler and another is a Hall effect sensor, that is magnetic field sensor. So out of these some devices we select here today, that is FET, field effector transistor. Another is a metal oxide semiconductor device, and gun diode. Because for BSc second year syllabus, these articles are there, and this is very useful for BSc second year students. So this FET, that is field effector transistor, is categorized in two FETs. One is N channel JFET and another is a P channel JFET. And again, there is some modifications. After modifications, we have to get a new semiconductor device, that is a MOSFET. And this MOSFET is again divided into two types. One is a E enhanced MOSFET. Shortly, this is called as a E MOSFET. And there are again two types. One is N channel E MOSFET and P channel E MOSFET. And other type, this is a depletion MOSFET, that is a D MOSFET. Shortly, we say that. And this is again N channel D MOSFET and P channel D MOSFET. So this is a construction or structure of this field effect transistor FET. This FET is a three-terminal device. One terminal is called as a drain. The out of drain there is called that terminal is called as a source, and middle terminal is called as a gate. So this field effector transistor is a unipolar transistor, means the charge carrier which are flowing through this transistor is depends on which type of channel is used. If we use N channel, then only electrons is flowing through this device. And when we choose here the P channel, then the holes are used to carry the current. So depending on the means only one charge carrier takes part in the conduction. That's why this is called as a unipolar transistor. Actually, in simple transistor, both the holes and electrons are take part into the conduction. That's why this is called as a bipolar junction transistor. But in field effector transistor, only one carrier is present, that is hole or electron. So the current flowing through this FET is controlled by the electric field. So this is the diagram of N channel FET. So this rectangular bar is called as a channel. So this channel is a N type, and at the center of this channel, P material is doped. See here, at the center of both the sides, at middle portion, P material is doped, and one terminal is taken from this P material, that is called as a gate. Internally, both the P materials are connected together, and only one single terminal we have to get, that is called as a gate. This one is the drain, and at the opposite of this drain there is a source. So this is the symbol of this N channel JFET. The arrow indicates, and this one is the symbol of P channel JFET. The arrow indicates the flow of current. At gate, in N channel FET, the arrow is in inward direction, and in second symbol, the arrow on gate in outward direction. So this gives the flow of current. So we discuss here about the working of junction field effect transistor. This is the circuit diagram of the to study the working of junction field effector transistor. Now this drain is connected to positive terminal of the battery, and source is connected to negative terminal of the battery. And at gate, we can the negative terminal is connected to this gate, and positive is connected to again source. So positive terminal is applied to drain with respect to source, and the reverse bias is applied between gate and source. Because we know here, for the working of this JFET, reverse bias voltage is applied at the gate. So when the negative terminal of battery is connected to P material and positive is connected to N material, then that is a reverse bias. So as P material is diffused with N channel, there is a formation of PN junction on both sides of the channel. So observe here. So this is a PN junction, one PN junction at one end, and at other side there is a second PN junction. So if we connect these two PN junctions in reverse bias, so the depletion layer is well penetrate inside this channel. So see here, this is a depletion layer of first PN junction, and this one is a second depletion layer, and in between these two depletion layers we have to get a small part in this channel to flow the current. So in reverse bias gate, depletion layer width increase with applied reverse potential, and the size of this depletion layer determines the width of the conducting channel. Reverse gate potential. So what happened here? The reverse gate potential control the drain current. Okay, so this is the drain characteristics. These characteristics represent variation of drain current with variation in a drain source voltage for constant gate source voltage. 1 minute, excuse me. So if we not applied any reverse voltage at the gate, means VGS is equal to 0, then we have to get a large amount of drain current flowing through this circuit. Okay, but as we increase the reverse potential on the gate voltage, the drain current starts to decrease. So the topmost second curve is for -1 volt. Again, this one is for -2 volt. The third is for -3 volt, and last one is for the -4 volt. Means we observe here, as a reverse gate voltage increases, the drain current flowing through this FET decreases. So as drain voltage is more than VDS, so see here what happened. Up to this point, as gate to source voltage increases, drain current is also increases. So this region is called as a ohmic region. But after this point, when VDS, drain to source voltage, increases, drain current becomes a constant. Okay, so this is called as a saturation region. Okay, and drain potential after which drain current remains constant, this is called as a pinch off voltage. So here red dotted line we have to get gives the pinch off voltage. After pinch off voltage, the drain currents remains constant. Now as drain current voltage is more than VDS, there is means here at last end terminal C here. So as again we increase the drain to source voltage, actually what happened, there is a breakdown occurs, means covalent bonds are breaks, and we have to get a large amount of current flowing through the this FET. So this current increases rapidly at the breakdown voltage, and we know that there are two breakdown. One is thermal, another is the avalanche breakdown, and these are due to the vibration of the electrons, minority electrons, and due to that covalent bond is broken up, and we have to get a large amount of current flowing through the circuit. Okay, so gate voltage with zero potential is called as shorted gate. So here upper curve is for the shorted gate. Shorted gate means we apply zero voltage, zero reverse voltage between gate and source. Now, what are the applications of this junction field effector transistor? So these FETs can be used as a linear device in amplifier or in logic circuits. These FETs, that is JFETs, are used for low noise amplifier, in buffer amplifier, cascade amplifier, analog switch, chopper, multiplexers, current limiters, and phase shift oscillator. So these are the some important applications of this junction field effect transistor. Now we go towards the metal oxide semiconductor transistors, that is MOSFET. So this MOSFET works on principle of a field effect transistor. It has three terminals, again, namely source, gate, and drain, like JFET. But in addition with these three terminal, there is a fourth terminal called as a substrate. So in MOSFET also, gate voltage control the drain current. In field effector transistor, gate voltage control the drain current. In MOSFET also, gate voltage control the drain current. Now at gate, now see what is the difference between FET and MOSFET? In FET, at gate we can apply only reverse bias voltage, but in this MOSFET we apply positive voltage also and negative voltage also. म्हणजे forward bias or negative bias, both voltages we apply at the gate of this MOSFET. At gate, positive or negative voltage is applied. This is main difference in between FET and MOSFET. So there are some two types of MOSFET. One is depletion type MOSFET. This depletion type MOSFET has again two type. One is N channel depletion MOSFET. Another is P type depletion MOSFET. And the second type is enhancement MOSFET. That is, this is again two type, divided into two type, N channel enhancement MOSFET and P channel enhancement type. So we discuss here about the N channel depletion MOSFET. So the construction of a MOSFET is similar to FET, and oxide layers here, this red oxide layer is deposited on the substrate to which gate terminal is connected. Now again, here this is one metal bar, and this is a semiconductor material, N material. But at only one end of this middle, P material is doped, and opposite to this P material, P semiconductor material, that is metal oxide is deposited here. See here, this red color shows the metal oxide deposition on the other side, and this one is the metal contact, and from this metal contact one terminal is taken here, that is called as a gate. Means at one end, at the middle portion of this one channel, there is a metal oxide deposition, and another end there is a P-type material doped. So this is called as a substrate. The terminal taken from this P material, semiconducting material or doping material, is called as a substrate, and the terminal taken from this metal oxide that is called as a gate. Okay, so this is a MOSFET is a four terminal device, and the region between source and drain, this is again also called as a channel. At one end of the channel, drain terminal is taken, and at the other opposite to drain, the terminal is called as a source. So the opposite to P channel depletion MOSFET means for P channel depletion MOSFET, this channel is a P type material, and here at middle portion, N channel material is doped, and opposite to this N material, metal oxide layer is there. So the construction for N channel and P channel is same, but the difference is the channel, that is P type or N type. Now these are the symbols of this N channel depletion MOSFET. So this portion, this gap shows that this is a metal oxide, and the central part is a substrate, and this source both are connected together. And this arrow again shows the flow of current, and this one be the symbol of the p channel depletion MOSFET, the current flow in outward direction. So here this is a n channel, 1 minute. So this mode of operation is called as depletion mode. Now working, how to work the MOSFET. So substrate, this substrate is connected to the source. So it reverse bias the PN junction, and depletion layer is extended in channel very well, and electron pass through this narrow channel. So observe here, this drain is connected to positive of the battery, and this source is connected to negative terminal of the battery, and this p material, that is substrate, is also connected to source, that is n material of the that is n negative terminal of the battery. But observe here, this gate this gate is connected to negative terminal of the battery. So what happens here, this gate due to this metal oxide, this forms one capacitor here, one terminal of this capacitor is a gate, and another terminal is this another plate is forms here the n channel. So when negative terminal is connected to gate, these negative ions forms the positive carriers or positive ions on opposite sides of this channel. So gate is insulated from the channel due to metal oxide. So gate and channel forms a capacitor with metal oxide as a dielectric. Okay, so we know the idea. So you understand, yes? This gate and channel forms a capacitor because in between gate and channel there is a insulating material, that is metal oxide. So the negative voltage on the gate induce positive ion layer in part of channel. So n channel electrons are depleted. So what happens here? This drain attracts the positive electrons which are from the emitted from the source. But what happens here, some of the electrons forms that is recombined with these holes, and drain current reduces. So this is the characteristics curve of the MOSFET. So observe here, this one be the drain current, and this is the voltage between drain and source. So at drain we can apply positive and negative voltage. So when positive voltage is applied at the gate, what happen? The negative ions are deposited on the n channel, and so all this drain attracts electrons from this source also, and from this creating ions also negative. So the drain current increases. So observe this, as positive voltage on the gate increases, drain current increases. But when negative voltage on the gate increases, so drain current decreases. So see here, when we apply -1 volt, the drain current decrease. Again, if we apply -2 volt at the gate, again drain current decreases. So in this way, we can apply positive and negative voltage on the gate. As gate is positive, then current flowing from the drain current increases, and when gate is at negative potential, the drain current decreases. So this mode of operation is called as a depletion mode. If the positive voltage applied on gate, the positive charge on the gate induce negative charge in the N channel. So number of conduction electron in N channel increases and drain current will be increased. And positive gate voltage increase or enhance the conductivity of the channel. Now N channel enhancement MOSFET. So two regions separated by distance of 25 micrometer with heavily doping concentration are diffused on lightly doped surface of p-type. Those N regions are encapsulate the terminals drain and source. So over the surface, a thin layer of insulation called silicon dioxide is developed. The hole made on this layer established aluminum contacts for the terminal source and the drain, and this layer of conduction acts as a terminal gate. It is a lead over the silicon dioxide and on the entire area of the channel, but it does not have any physical channel for this conduction. So see here, this is the p-type enhanced MOSFET. So instead of so here, this p region is fully in this middle portion. So there are three layers. The first layer is p material, the second layer is n material, and third layer is again p material. So this is a p channel. Similarly, this is n channel. So this is a p channel. The first layer is n material, the middle layer is p material, and the lower level is again n material. So this one is the p channel MOSFET, and this one, first one, is the n channel MOSFET. So this is the enhancement MOSFET. So from now, observe here at the topmost of this p layer, there is a one metal contact, and one terminal is taken from this metal contact, that is called as a drain, and from other opposite end, means at lower portion of this p material, one again terminal is taken, that is called as a source. But you observe here at the middle portion of this n layer, one end this metal oxide is deposited, that is called as a gate, terminal taken from this metal oxide called as a gate, and opposite to this gate at n material, one terminal is again taken, that is called as a substrate. So how to operate this? So induce the n channel positive polarity of the gate to source voltage is required, and as a large amount of voltage must be applied at the terminal gate for this operation. And if the voltage applied at the terminal gate to source is zero, the enhancement MOSFET does conduct, and this can be reason it is initially off condition. So actually, this is the construction of this n-type MOSFET. Now the minimum gate source voltage that creates the n-type inversion layer is called threshold voltage. This is a minimum voltage we can apply to the source, gate to source voltage. Whatever may be the layer produces, that is called as inversion layer. And that is called when inversion layer is formed, that voltage is called as threshold voltage. And when the applied amount of voltage at the gate terminal exceed the threshold voltage, the drain current will flow through the circuit. So this one is this threshold voltage is a minimum voltage which can apply. At that voltage, the drain current starts to flow through the circuit. Now when the positive amount of voltage applied at the drain source by keeping the gate voltage as 0, then p type of substrate and two n regions behaves like a two pn junctions. So see here, observe here, we have to get a two pn junction. in between P and N material, one PN junction, and at below side, in between N and P region, there is again one PN junction. Means when gate voltage is 0, and if we apply some voltage here at the substrate, means we have to form here the two PN junction in between these three layers. So this makes both the junctions reverse bias, means when negative terminal at P channel is applied and these drain and source are connected to battery as a positive, so there is a formation of reverse bias, means both the junctions are reverse bias and leakage current tends to flow through the circuit. Means whatever may be the current flowing through the circuit, that is very, very small. Why? Because both the junctions works in a reverse bias. And whatever may be the current flow, that is very small, that is due to the minority charge carriers, and that is called as a leakage current. Now, if the voltage applied at gate is made positive, the minority carrier present in substrate of p-type, that is electrons, get attracted to positive potential of terminal gate. So these negative charges carries get accumulated below the terminal of the gate, and if we further increase the gate to source voltage, will deposit more amount of carrier called the electron. So the use of dielectric prevents the movement of these electrons across the layer of the silicon dioxide, and this accumulation results in the formation of the N channel amide drain source. This leads to generate drain current flowing through the channel, and this drain current is proportional to the resistance of the channel, which is further depends upon the carrier attracted towards positive terminal of the gate. So this one is the drain characteristics of the MOSFET, means this is the voltage between VDS, and this one be the drain current. Now, what are the applications of this MOSFET? So these MOSFETs are very used in a digital integrated circuit such as a microprocessor. These MOSFETs are used in calculators also, for in logic gates, that is logic CMOS gates, for the memory store. These MOSFETs are used. These are again used in analogous switches. MOSFET devices also applied in audio frequency power amplifier for public address system. Again, these MOSFETs are used in amplifiers. These are used in applications of power electronics and switch mode power supplies, uses in oscillators in radio system, and in inverters also these MOSFETs are used, and the last use is audio mobile sound system in sound reinforcement system. So these are the some applications of this MOSFET. Now gun diode. This gun diode is a two-terminal semiconductor device. Gun diode is a transfer electronic device which is composed of only one type of semiconductor, that is N-type, and utilize the negative resistance characteristics of to generate the current at high frequency. Actually, these gun diodes are used for the microwaves device. This is gun diode is a microwave device. Now it is used to generate radio frequency and microwave frequencies. The p-type semiconductor is not used because it consists of fold as majority carriers. Means only N-type material is used for this gun diode. Now gun diode is made up of N-type semiconductor. This is made up of three layers. Actually, this gun diode is made up of three layers of the N-type semiconductor. Means all these three layers are of this N-type semiconductor. Only difference is for the doping. The doping levels of these three layers are different. Among these three layers, the topmost and the bottommost are heavily doped, while middle layer is lightly doped. So see here, this topmost N material is heavily doped. This lower layer is also heavily doped, but this yellowish portion, middle portion, is lightly doped. And on the upper side there is a metal contact, and at lower side is again metal contacts are there. That is for terminal taken from this gun diode. And at the lower portion there is a heat sink to absorb the heat whatever will be the generated. So metal contacts are provide on extreme layers. The heat sink prevents diode from excessive heat and damage. So one terminal of this gun diode is called as a anode, and another terminal is called as a diode. The middle portion of material is lightly doped, and the width of this is 10 micrometer. So this one be the construction, and this is the symbol of the gun diode. Now the gun diode is not PN junction diode because there is no P region, or P material is not used in the gun diode because due to that minority layers, majority layers, only N material is used. It is called diode because of involvement two electrodes. Because again, this gun diode has two electrodes. That's why the name given as a diode. The active region is the middle layer of the device and is 6 to 18 micrometer long. So the middle portion is very small, that is 6 to 18 micrometer long. The potential gradient will fall when current pulse transfers in the active region, which blocks another pulse to form. Means only one pulse at a one time is passing through this region. The next current pulse will forms only when the previous current pulse has travels the entire active region. So in such way, thickness of active region modified the frequency at which the device is working. So I told 10 micrometer thickness forms a 10 gigahertz frequency here. So the frequency is depends on thickness of the active region of this gun diode, that is middle region. Now in gun diode there is a valence band, conduction band, and one more band near to the conduction band. Now the current through the device increases because electrons move from valence band to the conduction band, and the current through the device starts decreasing because electrons in conduction band move to band above the conduction band. So in this gun diode, the current increases also and decreases also. So the effective mass of electron starts increasing, and thus mobility starts decrease, due to which current starts decreasing, and this creates the negative resistance region in the diode. So in gun diode, negative resistance region is created. So in this negative resistance region, the current starts increasing with the fall in voltage, and will starts decrease with increasing voltage. So observe here, the current in gun diode starts to increase with applied DC voltage, but here at threshold point, the voltage increases but current decreases. And after that, due to the current falling from the conduction to another conduction band, the current increases again with the voltage increases. So this is the maximum operating limit. So this point shows the maximum, means from this point to this point, this region is a operating limit of the gun diode. So what are the applications of this gun diode? Gun diodes are used as oscillators and amplifiers. They are used in radio communication, military and commercial radar sources. These gun diodes are used as fast controlling equipment in microelectronics for modulation of laser beams. It is used in tachometers. These gun diodes is used in sensor for detection in transpass detecting system, in door opening system, and safely system also. It is also used extensively in microwave relay data link transmitter. So we cover today here the gun diode, field effector transistor, MOSFETs, again N-channel FET, P-channel FET, enhancement MOSFET, and depletion MOSFET. So I am very thankful to Dr. L.B. Zadwar, Dr. Bhosle sir, Dr. S.R. Kamble sir, to invite me such an event for this lecture series. So thank you. Thank you very much.
Thank you, sir. Thank you so much for this expressive and important, fruitful discussion on the topic of semiconductors. I thank you, Professor Dr. B.B. Kaude, sir, for delivering such a nice talk for everyone. Thank you, sir. Thank you so much. Okay. Thank you.
Okay. जाधवर सर ठेवू का?
हो सर, जाधव सर सध्या कनेक्ट नाही आहेत.
ओके ओके, नो प्रॉब्लेम.
हो सर, थँक्यू सर.
ओके, लिहू.
हो.
ओके ओके.